Hi, in this video we are going to talk about Fourier Series Expansion. Fourier series is an infinite series that is used to represent a periodic function in terms of sines and cosines. Now if f of t is a periodic function with period 2p, then f of t is equal to a sub 0 over 2 plus the summation of a sub n times cosine of n pi t over p, where n is from 1 to infinity, plus the summation of b sub n times sine of n pi t over p, where n is from 1 to infinity. And these a sub 0, a sub n, and b sub n are called the Euler Constants. This is the Fourier series expansion. Now let's go to the formulas in finding these Euler constants. First, we have a sub 0. A sub 0 is equal to 1 over p integral of f of t dt with limits from t sub 0 to t sub 0 plus 2p. T sub 0 is the initial point of the interval. A sub n is equal to 1 over p times the integral of f of t cosine of n pi t over p dt with limits from t sub 0 to t sub 0 plus 2p, where n should not be equal to 0. And lastly, we have b sub n equal to 1 over p times the integral of f of t sine of n pi t over p dt with limits from t sub 0 to t sub 0 plus 2p. Again, 2p is 1 period and n should not be equal to 0. Now let's go to the types of periodic functions. First, we have even periodic function. F of t is an even function if it satisfies these conditions. First, f of negative t is equal to f of t. Next, the graph of the periodic function f of t is symmetrical with respect to the vertical axis. So the function that can be seen on the right side of the Cartesian plane is the same to that function that can be seen in the left side of the Cartesian plane. Now let me do this sketch for you to visualize an example of an even periodic function. This sketch shows you a periodic function that is symmetrical with respect to the vertical axis. We have negative p to p, an interval for one period of the function. So 2p here as one period is equal to 4. Now, if the given periodic function is an even function, these are the Euler constants. B sub n is equal to 0. And to determine a sub 0, it is equal to 2 over p times the integral of f of t dt with limits from 0 to p. And for a sub n, it is equal to 2 over p times the integral of f of t times cosine of n pi t over p times dt with limits from 0 to p. P here is the upper limit, which is equal to 1/2 of the period. Since b sub n is 0 and we have values for Euler constants a sub 0 and a sub n, our Fourier series expansion for even periodic function is f of t equal to a sub 0 over 2 plus the summation of a sub n times cosine of n pi t over p. N is from 1 to infinity. This Fourier series expansion is also known as Cosine series expansion. The next type of periodic function is odd periodic function. How do we know if a periodic function is an odd function? F of t is an odd function if it satisfies these conditions. First, f of negative t is equal to negative f of t. Second, the graph of the periodic function f of t is symmetrical with respect to the origin. To better understand this type of periodic function, let me show you this sketch. Considering that one period of a function at the middle of the Cartesian plane, it passes through the origin. This shows f of negative t is equal to negative f of t. Thus, showing you the graph is symmetrical with respect to the origin. 2p here is equal to 4. Now, if the given periodic function is odd function, the value of the Euler constants a sub 0 and a sub n is 0. And the formula to determine b sub n is equal to 2 over p times the integral of f of t times sine of n t dt with limits from 0 to p. Upper limit p means 1/2 of the period. Since we don't have values for a sub 0 and a sub n, our Fourier series expansion is f of t equals the summation of b sub n times sine of n pi t over p. N is from 1 to infinity. And we can also call this Fourier series expansion as sine series expansion. Now let's have the first example. Find the Fourier series expansion of the periodic function whose definition is f of t is equal to 1 minus t from 0 to 1, 0 from 1 to 2, 3 minus t from 2 to 3, and 0 from 3 to 4. Let's sketch first to determine whether this periodic function is even, odd, or neither even nor odd periodic function. As you can see, when t is from 0 to 1, the value of the function is 1 minus t. So you have an intercept equal to 1, slope is negative 1. So this is how you sketch 1 minus t. And from 1 to 2, the value is 0. From 2 to 3, you have a negative slope and intercept equal to 3. So this is how you sketch this line. And from 3 to 4, the value is 0. Now take a look at the given periodic function. So observe whether this function is symmetrical with respect to the vertical axis or symmetrical with respect to the origin. Since you can see from 0 to 1, you have a function equal to 1 minus t, and from negative 1 to 0, you have a function equal to 0. So this is neither odd nor even periodic function. So we should put a note here in our solution that this f of t is neither even nor odd periodic function, so that we may be able to know what we are dealing with and what Euler constants need to be determined. So in this case, we are to utilize the formulas for finding a sub 0, a sub n, and b sub n. So for a sub 0, we use 1 over p times the integral of f of t dt with limits from 0 to 2p, or t sub 0 to t sub 0 plus 2p. In our given, p is equal to 1 and 2p is equal to 2. So we plug in the formula 1 over 1 times the integral of f of t dt with limits from 0 to 2. So this interval 0 to 2 has different values of the functions. So from 0 to 1, the value of the function is 1 minus t times dt plus from 1 to 2, the value of the function is 0. So we can cancel this part. We are left with the integral of 1 minus t. So integral of 1 times dt is, we write t. Integral of negative t dt is t squared over 2 with limits from 0 to 1. Now we apply the limit, upper limit first minus the lower limit. So 1 minus 1 squared over 2. Applying lower limits, so we have 0 minus 0 squared over 2. Basically, this term is 0. Now a sub 0 is equal to, so 1 minus 1 half is 1 half. This is our a sub 0, and now let's proceed to finding for the value, or the value of a sub n. A sub n is 1 over p integral of f of t times cosine of n pi t over p dt with limits from 0 to 2p, or t sub 0 to t sub 0 plus 2p. Again, 2p is 1 period, and that is equal to 2. So 1 over 1 times the integral of f of t cosine of n pi t over 1 dt with limits from 0 to 2. And we know that from 0 to 2 interval, we have two different values of the function. So 0 to 1, it's 1 minus t multiplied by cosine n pi t dt. And for the second term, we have 1 to 2 interval with a function equal to 0. So we can cancel this 1. Next step is to integrate 1 minus t cosine of n pi t dt using what technique? Algebraic function multiplied by trigonometric function. So we can use integration by parts. So we let u equal to 1 minus t and dv equal to cosine of n pi t dt. So in this left column, you are going to differentiate. On the right column, you are going to integrate. So differentiate 1 minus t, it's negative 1. Integrate cosine of n pi t, you have sine n pi t times the neutralizing factor 1 over n pi. Differentiate negative 1, that is 0. Integrate the right column, so you have cosine n pi t times negative of 1 over n pi squared. That is due to the neutralizing factor. Again, follow the right notation or the signs for integration by parts. We have a sub n equal to 1 over n pi times the quantity 1 minus t, sine of n pi t minus minus times negative. So you have minus the quantity 1 over n pi squared times cosine of n pi t with limits from 0 to 1. The next step is to apply the limits. Upper limit first. So 1 minus 1, our first term therefore is 0. And then applying the lower limit, so 1 minus 0 times sine of, sine of 0. So we can cancel this 1. And for the second term, minus the quantity 1 over n pi squared, upper limit sa cosine of n pi times 1, minus the lower limit, 1 over n pi squared cosine of 0. And cosine of 0 is equal to 1. Then we simplify. Just to make sure, sine of 0 is equal to 0, cosine of 0 is equal to 1. Therefore, our a sub n is, distribute the negative sign here. So we write first the positive 1. So 1 over n pi squared minus 1 over n pi, quantity raised to 2, cosine of n pi. Now we can still simplify cosine of n pi. Let's evaluate cosine of n pi. Change the color. Okay, so when n is equal to 1, we have cosine of pi, and the value is negative 1. If n is equal to 2, cosine of 2 pi is equal to positive 1. When n is equal to 3, cosine of 3 pi is equal to negative 1. And finally, if n is equal to 4, cosine of 4 pi is equal to positive 1. So take a look at the pattern. It's negative, positive, negative, positive. Therefore, we can say that cosine of n pi is equal to negative 1 raised to n. So if the power is odd, the value is negative. The power is even, the value is positive 1. Now, our a sub n is, so we write first, the quantity 1 over n pi squared minus the quantity 1 over n pi squared times cosine of n pi. We factor out 1 over n pi squared, rewriting, so bracket times, or bracket 1 minus cosine of n pi, and cosine of n pi is negative 1 raised to n. Therefore, our a sub n is 1 over n pi squared times the quantity 1 minus negative 1 raised to n. Now that we have a sub n, so our last Euler constant will be b sub n, and the formula is 1 over p times the integral of f of t sine of 2 sine of n pi t over p dt with limits from 0 to 2p, or t sub 0 to t sub 0 plus 2p. I'm always saying 0 because the lower limit is 0 for that case. So 0 to 2 interval. This interval has two different values of the function. From 0 to 1, you have a function equal to 1 minus t multiplied by sine of n pi t dt. And for the interval 1 to 2, the value of the function is 0. 0 times sine of n pi t will give us 0. So basically, we can cancel this second term. Now to solve further, we need to use integration by parts technique to solve the integral of 1 minus t sine of n pi t dt. So the left column is differentiation, and for the right column, you are to integrate this one. Integrating sine, you have negative cosine with neutralizing factor. And then on the left column, you are to differentiate until it becomes 0. So that ends your integration on the right column. The pairing is u times v minus u times v in that column. So our b sub n is equal to negative 1 over n pi times 1 minus t cosine of n pi t with limits from 0 to 1 minus the next factor or product is 1 over n pi squared times sine of n pi t with limits from 0 to 1. Now we apply the limits. Upper limit is 1, so 1 minus 1 is 0. For the lower limit, we have 1 over n pi times cosine of 0. Cosine of 0 is equal to 1. For the second term, we have the quantity 1 over n pi squared sine of n pi times 1 as the upper limit. So we can say this is 0. Later, I'll show you the proof why sine of n pi is equal to 0. And for the lower limit, you have 1 over n pi squared sine of 0 is equal to 0. So here's the proof that sine of n pi is equal to 0. As we know that cosine of 0 is equal to 1. Now for n equal to 1, sine of pi is equal to 0. For n equal to 2, sine of 2 pi is equal to 0. And for n is equal to 3, sine of 3 pi is still equal to 0. Therefore, we can say that sine of n pi is equal to 0. Now we simplify. We can cancel the second term, so we are left with negative times negative, you have positive. 1 over n pi times cosine of 0, which is 1. So our b sub n is 1 over n pi. We were able to solve for a sub 0, a sub n, and b sub n Euler constants. The next step is for us to write the Fourier series expansion. So recall all the values. We write a sub 0 is 1 half, a sub n is 1 over n pi quantity raised to 2 times 1 minus negative 1 raised to n. B sub n is equal to 1 over n pi. And the Fourier series expansion is so f of t equal to a sub 0 over 2 plus the summation of a sub n cosine of n pi t over p with n from 1 to infinity plus the summation of b sub n times sine of n pi t over p, where n is from 1 to infinity. Now we plug in the values of these Euler constants. Remember that p, or half of the period, is 1. So f of t is equal to 1 half over 2 plus the summation of a sub n is, okay, you copy 1 over n pi squared. Just plug in the value of these Euler constants to that formula or to the guide. Times cosine of n pi t over 1 plus the summation of the value of b sub n is 1 over n pi times sine of n pi t over 1. Now we can put the constants before the summation. 1 half divided by 2 is 1/4 plus, so you put 1 over pi squared before the summation, or the sigma, the symbol sigma. So anything after the sigma symbol has n, so you apply the value of n for that particular expression. So 1 over pi will be put before the summation symbol, and then inside the summation symbol is you have 1 over n times sine of n pi t. Now this is our Fourier series expansion for a periodic function that is neither even nor odd function, or you can simply write in this format without the summation. So we have 1/4 plus, so in this case you have to assign the values of n from 1 up to maybe 3 and then put ellipsis. So here for n is equal to 1, you have a coefficient 2 times cosine of pi t when n is equal to 2. So cosine of the cosine 2 pi t will be removed from the term because of its coefficient equivalent to 0, and so on. So just put ellipsis in there. Okay, the same with the last term. So removing the summation, this is how you write the one that has the b sub n Euler constant. Now we have the next example. So for our example number 2, we are given with a sketch. Let us examine the sketch, whether it's an even periodic function, an odd periodic function, or neither even nor odd periodic function. Okay, similar to our example for the odd periodic function. So as you can see, Let's take a look at that one period of the function in the center of the Cartesian plane. So the function, or the value of the function from the right part of the Cartesian plane is equal to the negative of the left part of the Cartesian plane. And this function passes the origin, okay, writing 2p or one period of the function, we were able to see that 2p is equal to 4 and showing you negative p to p interval. Since this is special case, f of t is odd periodic function because the graph shows that it is symmetrical with respect to the origin. And because of that, two of the Euler constants are 0. And what are these Euler constants? You can say that. So we define first the given periodic function in one period. That is from negative p to p. So negative p is negative 2. So f of t is equal to the value of the function from negative 2 to negative 1 is positive 1. And the value of the function from negative 1 to 0, you have a line with negative slope, but you can actually extend it up to 1 because the line extends. So the value is negative t with intercept 0. And from 1 to 2, the value of the function is negative 1. And take note, as I mentioned earlier, two of the constants, Euler constants will be 0, and that is a sub 0 and a sub n. Now, what you're going to do is to solve for the remaining Euler constant, and that is b sub n. So this is the formula that you're going to use. 2 over p integral of f of t sine of n pi t over p with limits from 0 to p. Again, so rewriting that formula, 2 over p integral of the limits is 0 to p, or 1/2 of the period, f of t times sine of n pi t over p dt. So p is 2. Plugging into that formula, so 2 over 2 times the integral of, the limit is 0 to 2, so f of t sine of n pi t over 2 times dt. So we know that from that interval 0 to 2, there are two different values of the function. So what are these? So let me just sketch again. From 0 to 2 interval, you have a negative slope line. So negative t is the value of the function from 0 to 1. And from 1 to 2, you have negative 1. This is what I meant with two different values of the function. So therefore, our b sub n is, from this interval 0 to 2, we can write b sub n equal to, from 0 to 1, you have negative t times sine of n pi t over 2 times dt. Plus, for the interval 1 to 2, you have a function equal to negative 1 times sine of n pi t over 2 dt. Now we deal first with the first term. We can solve this integral using the technique integration by parts. So our u is negative t and our dv is sine of n pi t over 2 times dt. Differentiate negative t, that's negative 1. Integrate sine of n pi t over 2 is, you have negative cosine of n pi t over 2 times the neutralizing factor of 2 over n pi. And finally, you integrate for the last time because the derivative that you have seen on the left column is 0. So the answer to the first term of our b sub n is, going back here, so you have negative t times negative 2 over n pi, and that is positive. So 2 over n pi times t cosine of n pi t over 2 with limits from 0 to 1 minus 2 over n pi squared times sine of n pi t over 2 with limits from 0 to 1. So this is the result for integrating the first term. Now we go to the interval 1 to 2. So integral of sine of n pi t over 2, just a direct integration using the formula that you have learned in integral calculus. So you have here a neutralizing factor equivalent to 2 over n pi, and we can plug in here. It's negative 2 over n pi times cosine of n pi t over 2 with limits from 1 to 2. The next step is to apply the limits. Upper limit minus the lower limit. So here in our first term, you have 2 over n pi times 1 cosine of n pi times 1 over 2 minus the lower limit, which is 2 times 0. So you have 0 for this term. And then for the second term here, applying the limit, so 2 over n pi squared, sine of n pi times 1 over 2 minus the lower limit, 0. So sine of 0 is 0. And for the last term, applying the limits 1 to 2, upper limit is 2, so 2 over n pi cosine of n pi times 2 over 2, so that's why you have cosine of n pi there, minus the lower limit cosine of n pi times 1 over 2. So here I'm showing you why cosine of n pi, because we are able to cancel 2 there. Distribute 2 over n pi, we can be able to cancel the first term and the last term because they have unlike signs. So b sub n therefore is equal to negative of 2 over n pi squared times sine of n pi over 2, and you have plus 2 over n pi cosine of n pi. Since we already determined cosine of n pi equal to negative 1 raised to n, so we can replace by that value. Our b sub n factoring out 2 over n pi is equal to, or will result to this equivalent. Now, for the final step is to write the Fourier series expansion of this odd periodic function, or we call this the Sine series expansion. So for odd periodic function, remember that a sub 0 and a sub n are equal to 0. We have b sub n equal to 2 over n pi times the quantity negative 1 raised to n minus 2 over n pi cosine of n pi over 2. Now for our expansion, we have 2 over pi, so we put the constant before the summation. Summation of 1 over n times the quantity negative 1 raised to n minus 2 over n pi sine of n pi over 2 times sine of n pi t over p. P is equal to 2. So this is now our final answer, the sine series expansion for the odd periodic function. And for the final example, this will be your seat work number 11. So let me write the given first, and we'll examine what type of periodic function this given is by observing the sketch. I'll give you hints. I'll give you the starting part of your solution, what Euler constants will be determined, and the values of these Euler constants for you to check your solution as well. So let me draw first the graph. This is actually similar to the example that I have presented earlier. Okay, so take a look at the given function. Now, the value of the function at the right side of this Cartesian plane is equal to the value of the left side of the Cartesian plane. So it means that this given periodic function is symmetrical with respect to the vertical axis. If you try to fold this paper containing these functions or these drawings, you can be able to match it. They are in symmetry. So you can label the negative p to positive p interval as your guide later in defining this periodic function. So you write a note here. F of t is an even periodic function because of what? Because the graph is symmetrical with respect to the vertical axis. So in this case, if the given periodic function is even, one Euler constant is equal to 0. And what is that? So b sub n is equal to 0. So in here, you are to solve for a sub 0 and a sub n. So the formula to use is 2 over p times the integral of f of t dt with limits from 0 to p, 1/2 of the period. The same with a sub n, but you have a cosine function in your integrand. Now we define the periodic function in one period. Okay, this will be our guide in writing the functions later. So from 0 to 1, the value of the function is, you have a positive slope, intercept is 0, so the value is t. And from 1 to 2, you have, actually from 1 to 3, the function is equal to positive 1. If you continue that one period, so from 3 to 4, you have a function which has a negative slope and intercept is positive 4. Now for our a sub 0, the formula is 2 over p times integral of f of t dt with limits from 0 to p. Our p is, or 1/2 of the period is 2, so the interval will be 0 to 2. So we have two different values of the functions for this particular interval. So from 0 to 1, you have t, and from 1 to 2, the value is 1. And you just continue solving these Euler constants a sub 0 and a sub n. So for you to check your answer, a sub 0 is 3/2. A sub n is equal to negative 4 over n pi squared plus 4 over n pi squared times cosine of n pi over 2. And since your b sub n is 0, you write your final answer, the expansion. And we call it the cosine series expansion.